So you have all these different derivative rules that keep you from having to do the actual definition of the derivative, which if you can imagine all that definition of the derivative all the time, all that work, it would be a road graph. So these shortcuts are golden. They really save you some time. We know, for example, that when you take the derivative of a sum, you can actually take each derivative individually, then add later. We also knew the power rule in there. So for example, when you take the derivative of a sum, you could just take the derivative of x squared, which is 2x, and the derivative of x cubed, which is 3x squared. You with me? So, this is going to sound wordy, but it's true. The derivative of the sum is the sum of the derivatives. Cool? The question then would be, if you had a product, is it true that if you take the derivative of a product, is it the product of the derivatives? Is that true? That's the question of the day. For products, can you do the same thing? Can you just say, take the derivative of that, take the derivative of that, multiply them together? Well, this is actually a great case here. Take the derivative here, and that'll tell you whether that rule is cool or not. This really is the derivative of x to the fifth, right? Do you agree? All right. What should the derivative of x to the fifth be? 5x to the fourth. All right. Now let's see if our hypothesis or idea works, if it gives you the right answer. The right answer should be 5x to the fourth. That is the right answer. What's the derivative of x squared? Hello? 2x. What's the derivative of x cubed? 3x squared. So if I take each individual derivative, I actually get 6x to the third. So, is our theory correct? If I take the derivative of a product, I can just take each derivative and multiply later? No, that is not true. That does not work. Products are different. Products are different. You can't just say, oh, I'll take this derivative and that derivative and multiply together. You can't do that with products. It doesn't work. Are you with me? All right. You cannot take the derivative of each term, then multiply. That does not work. Now then, so I debate how much. I need to ask you a question. How many questions do you have on last night's homework? A lot or not too many? Okay, then I'm going to have to change this lesson a little bit. I normally am not a big fan of, here's the theorem, memorize it, I don't care if you don't know where it comes from. I don't teach that way. I teach, you need to know where it comes from. If you don't know why, you don't know jack. That said then, the proof of the product rule or where it comes from is a little bit hairy, and that's what this whole section is. So, if I have time, I'll come back to it later. But for now, gosh darn it, I'm going to give you the product rule on the short. Okay? If you take the derivative of a product, by a product I mean two functions, f of x and g of x. And I'm not even giving the arguments f of x and g of x. Okay? Then the rule is you do take each guy's derivative. You are going to need to know each guy's derivative, but you take terms. And so it's more like first stays the same, so f stays the same, times the derivative of the second, which is g prime. And then add, second stays the same, so g, times the derivative of the first. They each get a derivative taken. But while that's happening, the other one stays the same. All right, so the product rule in plain old English is first stays the same times the derivative of the second plus second stays the same times the derivative of the first. pretty easy rule to apply. We'll go to the back side and we'll play around with it and practice it some, and I think you'll do just fine. The proof of it's the hardest part for sure that I'm bypassing. All right, are you ready? So that's the rule and symbols, and it goes in action like this. Actually, let's go back to this question. Look back at that sample case then. If I take the derivative of x squared x cubed, using this new theory, okay, does this work? We know, again, that the answer is supposed to be, what was the answer supposed to be? 5x to the fourth, right? Let's show the product rule. Okay, so the product rule on this problem would be first stays the same, so x squared times the derivative of the second, which is 3x squared, plus second stays the same, x cubed times the derivative of the first, which is 2x. If you simplify that, that's 3x to the fourth plus 2x to the fourth. Those are like terms, so it is indeed 5x to the fourth. Okay, hi. Oh, wow. Okay, so let's look at a case that's not so polynomial-ish. This is a product. The minute you see a product, say, okay, I can't just do each derivative separately. I have to use this product rule. So first stays the same, e to the x times the derivative of the second, which is, what's the derivative of x cubed? 3x squared, and what's the derivative of minus 1? 0. Okay, derivative of a constant is 0. Plus, second stays the same, so that's x cubed minus 1 stays itself, times the derivative of the first. What's the derivative of e to the x? E to the x. Okay, now that is fine. I don't require that you do any more. Just in terms of multiple choice, a multiple choice sometimes might have e to the x factored out, and you might see something like 3x squared plus x cubed minus 1. I don't require that on the homework unless I specifically say you just need to have those algebra skills to choose multiple choices that might be different. You with me? Try the next one on your own then, please. Or the next two on your own. I'm with you in math and English. All right. Very good. All right. So, first thing is, this is test your name. It's off the show. No, we actually on the after school. It's like, take your answers. I am one of the here during the answers of other stuff. Also, here, the idea we're talking about is first thing you have to understand is that when you do a derivative of sum, you can keep each term separately. So if you're doing a derivative of sum, however, that's not how it's when you do products. And if I take the derivative of products, you can know the product rule is How we doing? Okay, so check your work here. First stays the same. So actually, let's go with that too. You have two choices. You can actually just leave 2 out front altogether and have the product rule inside. Or what I tend to think of is I'm just going to kind of lump that into the first function. And rather than think of the first as sine of x, I'm going to think of the first as 2 sine of x. You get the same answer either way, you'll see. So first stays the same. 2 sine of x times the derivative of the second. What's the derivative of cosine for tomorrow's test? Sine or negative sine? Negative sine. Plus second stays the same. Cosine times the derivative of the first. What's the derivative of 2 sine? 2 cosine. Okay, so anything that's equivalent to that, you're good. With me? Did that go okay? All right. How about this one? This one actually has 2 steps. You first take the derivative, then you have to substitute in or evaluate. So take the derivative first. First stays the same, so what's your first term? T squared plus 1. Times the derivative of the second, what's the derivative of t plus 9? What's t of the derivative of t to the 1? Or the derivative of t to the 1? Just 1. Plus, second stays the same. T plus 9 times the derivative of the first. What's the derivative of t squared plus 1? 2t, the constant, has a 0 derivative, right? At t equal 1 then, means I now have to get a numerical slope at a specific point, so I'm looking at something like 2 times 1 plus 10 times 2, so maybe 22. Do you agree? Okay. All right, now, we will always be practicing calculus on lots of levels. This is the analytical level, okay? Taking the equation and its derivative. Let's talk numerical or table or tabular. Would you try and give me the derivative of product FG at x equals 4? I still want you to show me the general derivative and then say at 4. So in other words, do it in 2 steps, please. Product rule, and then at the number. Let me try the one after that as well. Negative 17 looking for the first one, yes? Okay. Oh, shucks. How about the next one? What are you getting for that one? Anybody? -32-ish? Is what I got? Okay. Is this going okay? You with me? Great feedback. Thank you. I know exactly now whether I'm doing well or not. Super. I'm going to leave. I'm going to grade your test tomorrow. And when you get it back on Monday, there'll be nothing on it. Okay? I'm just going to say, yeah, how's that for feedback? Because that's what you're giving me right now. It's ticking me off, man. Give me some feedback, people. You got it? Good. Okay. You wouldn't like it if I give you a test with nothing written on it? No. Feedback, baby. All right. Go. Find a drip. Now I'm all worked up. Doing my day. Get to work. Not easy. If you're confused, please call me over. If you're confused, you might write that note down. When you go to gather F values or G values, you're actually looking for the Y value on the graph at that F. But when you're asking for a derivative value, well, then you're looking for the slope of the graph at that. The derivative values are the slopes, the function values are the Y's. You have your answer? Okay. So F at 3. When I say the product rule, I first need F at 3. That's the actual Y value on the F graph at 3. So here's the F graph. At x equal 3, the Y is 1. Okay, times G prime at 3. So go to the G graph, which is the red one. Go to 3. But now don't give me the Y, give me the slope at that point. What the derivative, G prime, is the slope at that point. What is the slope at that point? It's 1. So we're only 1 at that point. Okay? Plus G at 3. Go to the G graph, x equal 3. Am I gonna, then you give me the actual Y at that point. What is G at 3? 3. And F prime at 3 then is the F graph at 3. But I want the slope there. So what's the slope there? -1/3. Okay, so it's a mixture of gathering Y values and slopes at points and putting them all together. So that's 1 minus 1 or 0. Okay? Did you get a chance to do the other one or no? Give you a minute. Give you a minute. Okay. Thank you for the speaking. All right. All right, sorry about the delay. Okay, let's talk here. Um, so the derivative would be first stays the same. So what's 2 sine x stays? 2 sine x. Derivative of the first, derivative of the second is f prime. Plus second stays the same. F of x, or f, times derivative of the first. What's the derivative of 2 sine x? 2 cosine of x. Add x equals 0. Plug it in. 2 sine of 0. What's 2 sine of 0? Sine of 0, is that 0 or 1? 0. So I don't actually even need to sweat that. I don't really care what the derivative is there because it's going to 0 out anyway. Guess I could find out what is f prime at 1. F prime at 1 is, or f prime at 0, excuse me, is negative 1/3. It doesn't matter because it's going to 0 out. What about f at 0? What'd you say for f at 0? It's 2. That's the y value at 0 is 2. And 2 cosine of 0 is 2 times, what's cosine of 0? 1. So did you get 4? Yes? Okay. All right. That's the product rule. First stays the same times derivative of the second plus second stays the same derivative of the first. You should be fine. Usually students catch on really quick. Sometimes students in a week will forget, but they'll get it. All right. Would you get out, if you haven't already done so, yesterday's homework? I strategically only gave you some of the stuff because I didn't want it to be a gigantic copy test. So, let's see how we did on sheet 3 set 29. I'll give you a second to get that out. All right. So, how did it go? Good? All right. So, this is the kind of thought process I wanted you to show. I tried to model it here. You should start with the formula for what they're asking. Area of a circle is area equals pi r squared. Then you should show the differential idea generally and then derivatives specifically, okay? Now, when you do that, this guy here is the differential of the independent or the dependent variable. So in this case, I'll take dA, yeah? Then times the derivative of the function. Now this would be a prime, but not as a function of x like before. This one is a derivative as a function of r. So it should be a prime of r times dr. Right? Now, I'm not, I have at least a couple students that I'm writing it, but I don't have any freaking clue what it means. Okay, well, fair enough. This can actually be pretty easily explained. Think about it like this. A is this pi r squared, okay? There are two notations to the derivative. Just think this. Say I got Newton and Leibniz together. I could say the derivative is either dA dr, or the derivative is a prime of r, Leibniz notation or Newton notation, right? I mean, that's just derivative equals derivative. You with me? Just the two different notations. The step you're seeing then is that these are now split. dA then is the derivative times an amount of change in r would give you an amount of change in a. That's the idea that we're going to get to, is the change in a depends on the rate of change times an amount of change in r. All right? So we're just skipping that derivative step and going straight to the split. In this case then, specifically, what's the derivative of a? 2 pi r, right? Pi is a constant. The derivative of r squared is 2r, so 2 pi r, and then the dr. So that was your answer there. Cool? Why? Because the derivative itself should have been dA, dr is a prime. For the reasons we're going to talk about later, we actually want to move this over. So this should have been dA, dr. We moved dr over because we want to separate the differentials again. For now, do it, and I'll explain why later. Understood? Okay. So I will throw up the answers to the other ones. If you want to see the work for them, let me know. But the next one, for C, I guess it would be, do you have something like DC is 2 pi dr? Yay? Okay. For the one after that, do you have dA or ds if you use s for surface area? Is 8 pi r dr? Tell me if you disagree with any of these. Then dV is 4 pi r squared dr. D volume of a cube. I guess you could use a lot of different variables. You could use sides, edge, whatever. But if I used volume of a cube as x cubed, then my variables would be dV is 3x squared dx, or whatever your variable used. Surface area of a cube, you could say surface area of a cube is 2 times the area of the base plus the square root of the base times the height. That is a gigantic mess to take a derivative on. So it's much easier if you said the area is 6x squared, okay? A cube has 6 identical faces. Each one is x squared, so 6x squared is much easier. This can be shown to equal, come to this. It's easier if you start here. With that in mind, then, dA is 12x dx. How do we do that? Bene? Bene. Never mind. Is there another one after that? Oh, did I not? Oh, sorry. Do you have dy is 4e to the x plus, what's the derivative of sine 2? Is it cosine 2? Because it got you. Is the derivative of sine 2 cosine 2? It is not. Why not? Sine 2 is a number. It's a constant. Sine 2 is not a function. It's a constant. It's not the sine of x. That's a function. Sine of 2, that's a number. And so what's the derivative of a number or a constant? That should be 0. Okay? This then, 5x to the 3 halves, is a way to rewrite that. The derivative by power rule then would be 15 halves x to the 1 half. That says 1 half, not d2. Dx up. Does the derivative need to be in parentheses? Yes, it better be in parentheses. That's just good algebra. Okay, this. Estimating change using word problems. These are business calculus problems I pulled from a business calculus, okay? Marginal cost is the cost of producing one more. So, differentials to estimate the marginal cost. Let's start here, okay? The big idea is that dc dx is the same as the derivative c prime of x. You didn't have to write that. You could jump straight to dc is the derivative c prime times dx. Okay? The differential idea is the derivative. The differential is the derivative times the differential of the other. All right. So that said, then let's roll. What is the derivative of c? Zero plus 5 over x, or just 5 over x. That needs to always be done. In this case, that needs to be done at a certain number. These word problems, they'll usually say at what number? Well, at what x? 100. And dx is how much, x stands for the number you're going to produce. So dx stands for how the number you're going to produce is going to change. How much are we going to change the number of production by? 1. We want to know the cost of 1 more. And so the cost of 1 more would be 5/100 in dollars, that is 20 cents. That next one will cost 20 cents to produce. You follow? All right. 3, I don't remember how much I gave you on 3. 3, the answer is 0.8 pi cubic centimeters. Are you good, or shall we show where that's coming from? 0.8 pi cubic centimeters. Is that what you got?
Yes.
All right then. I heard a no. What was your delta V is dV. Now that's then the start of the show. dV, by all this idea, when you find the differential, it's the derivative and the differential of the other. Now in this case, it's a sphere, so the equation is 4/3 pi r cubed, right?
I'm just kidding my coffee.
Okay, cool. All right. Anybody need me to? All right, thank you for telling me. All right, let's go to this guy. How did that log domain go? What did you get? Did you get this, -7 to 0 or 9 to infinity? Yes? Okay. Let me know if you have questions on that. Yes? Okay. So, the idea very much if you use, I tried to give you a little hint, you're trying to figure out what x's are allowed. So, to get the what's allowed or the domain, make a sign chart for the inside of the log expression. Here, did I give you more direction in that? Okay. Sign chart for the inside. In other words, this must be positive for log to be cool. Okay? So start, in order to find where something's positive or negative, it helps to start by finding where it's 0 and then test around that. Because if it's 0 here, then it must be positive or negative around it. So if you take out a 2, or an x rather, and factor, this factors in 2, oops, what? What are the factors of 63 that combine to 2? Well, could combine to -2, right? X minus 9, x plus 7. So the zeros, this graph is 0, or the inside is 0 at 0, -7, and 9. Wait. All right, then the idea is that you place those on a number line in order from least to greatest, -7, 0, and 9. And then you take a representative number from each region and plug it in. Usually you want to look in the factored form. So if I plugged in -8, I'd get negative, negative, negative. 3 negatives multiplied would come out negative. That region then will be a negative in a log. That's bad. In the next region, a number between -7 and 0 could be -2. Negative, negative, positive. 2 negatives is a positive. This region is okay then, and so that's why you see it as part of my solution. Continue that sign test idea for all 4 regions. And then as far as the parentheses, why parentheses, not brackets? Because you can't equal 0, why not? Why can't it, it's 0 there, and why is that bad? Because log of 0 is bad. E to what power would be 0? None. There isn't one. Okay. All right. So that's the idea here. This guy, you would have, now this, it's asking you to sign chart the derivative, not the function, the derivative. So the first thing you should be doing is taking the derivative to cosine of x plus 1 equals 0. Find the zeros. Cosine of x is -1/2 at, hopefully your trig skills are solid, that's at 2 pi over 3 and 4 pi over 3. And then sign test from 0 to 2 pi over 3 to 4 pi over 3 to 2 pi. You could sign test. I imagine some people might have also looked at a graph and said, well, 2 cosine of x plus 1 would be something like shifted up 1 and stretch 2. So it might look something like this. Positive, negative, positive. You could do it that way too. Sign test effectively, though, in your region is, your answer to that should be 0. Okay. 0 to 2 pi over 3 and 4 pi over 3 to 2 pi. But let's talk parentheses or brackets. At 0, what's the derivative? Positive or negative? Positive. So I need to include that. That's a bracket. at 2 pi over 3, is it positive or positive, negative, or 0? Zero. So it's not positive there. The question is, where is the derivative positive? It's not positive at 2 over 3, so you should actually have brackets on the endpoints because the derivative is positive there, but not at those critical numbers. Okay, so your answer looks like that. If you got those endpoints, then you're the master. Good for you. This one is a bit of a trick question. What did you get for where is that guy positive? Or not that guy, the derivative. Where's the derivative positive? Everywhere. E to the x is always positive. You're adding 2, so that's always positive. If you mindlessly plowed ahead looking for zeros, hopefully without too far down the line, you said, wait a second, x is the natural log of negative 2. What? That doesn't work. And you probably said something's amiss. I hope. If your eyes are open. If you just mindlessly plowed ahead, then shame on you. Okay, this bad boy. This, I hope you recognize this as the definition of the derivative. It's the derivative of what? Yes, sine, exactly. Way to go, me. Which is cosine. The answer is B. Okay. This guy, a tangent to the line. This is on the test tomorrow. You should be able to do that on test. So that's what I got for an answer. Are we all good with that? Okay. I assume that's yes. All right. How about the next one then? Your answer to that is B. How'd that tangent line problem go? Good, good. Go over it or good? Go over it?
Yeah.
Look up for yourself, okay? You need to college it up here. All right, so let's go with the tangent line process. First, to do a tangent line, you need a point. It's very common for students to use the wrong point in this question. You definitely don't use 4.1 because it's ugly. That's the whole point of the question. Use a good point, 4. You should be using points that are clean to estimate the ugly. So as far as what point you use the clean one. 4. If 4 is put into that function, what's the y? 1/2. Okay. The slope comes from taking the derivative at the good point, not the derivative and just letting the derivative hang out, the derivative at the good point. So, what is the derivative of x to the negative 1/2 by power rule? Negative 1/2 comes down, x to the negative 3/2 at 4. That's pretty ugly. Let's proceed on and rewrite this. Negative 1 over 2. The negative exponent means denominator. The half means square rooting. And the 3 means cube. So all that algebra skill then takes me to the fact that the slope is 1/16 negative. Are you with me on the slope? Do you agree? Okay. So then write the equation of the tangent line. Y minus 1/2 equals negative 1/16 x minus 4. If that's out of nowhere, if you don't know where I'm getting at, ask now. That's point slope form. Okay. All right. Last but not least, then the question. They want you to estimate what would this curve be at 4.1. I definitely don't want to put 4.1 into there, so instead we're putting 4.1 into our tangent line we just made, because tangent lines are easy to use. Y equals 1/2 minus 1/16. I'm going to call this 4 and 1/10 because I got fractions going on. So 4 and 1/10 minus 4. That's 1/2 minus 1/16 of 1/10. That's 1/2 minus 160. That's what, 80, we'd have to multiply this by 80 over itself, so 80 minus 1 over 160, or, okay? Is that on this page? Yes, I think that's it on this page. This guy, 1.05, how did that go? Did that go okay? Go over that one, that did not go well. Okay, so this one is also the idea of using a tangent line. Now, first of all, then the point. Am I going to use negative 0.1 for the point or 0 for the point? 0. Use the clean point for your point. The point is 0. And what's the y at 0? 1 minus sine of 0 is 0 there, but square root of 1 minus 0, so 1. The point is 0, 1. Now the slope, this is where your calculator comes in. The slope is the derivative at the good point 0. If you have seen calculus before this year, then you could probably do that derivative by chain rule. But if you haven't seen calculus before this year, then you probably would want to use your calculator to find that derivative. The derivative is negative 1/2. Yeah? Now, if you don't know how to do that derivative, remember the idea is that you, in the Inspire, you go to Menu, in the home screen, you go to Menu, Calculus, Numerical Derivative, then it'll take you to a little sub-menu. You'll say use X. You want the derivative at 0, not negative 0.1, at 0, and then the first derivative. Then it'll take you back and you'll have to type in the function. When you do all that, it'll calculate the derivative for you, or actually it's estimating the derivative by taking 2 points within a 100,000th of each other. It doesn't actually know calculus. And so I get rounded to the nearest thousandth, negative 1/2. Okay? So your tangent line then is y minus 1 equals negative 1/2 x minus 0. I have my tangent. Now, how do I use it to estimate? Talk to me about plugging in. Plug in negative 0.1 in, and y is 1 minus 1/2 times negative 1/10, which is 1 plus 1/20th. That's 1.0. Okay? All right. 10. The curves. The solution was x equals 3/2. I didn't show the y's. X equals 3/2. How did this go? Do we need to talk about the thought process on this? Just parallel. Okay, so this is actually a good practice on problems that are very common in AP tests. They ask you to make deductions, okay? In this case, the deduction process would go like this. Curves have parallel tangents. You need to talk to yourself a bit. Well, parallel tangents mean same tangent slope, right? So the first thing I did is say, what is parallel? Well, that means same slope. Then I looked at, well, tangent slope. Where does tangent slope come from? In calculus, we find tangent slopes by taking, hello? How do you find the tangent slope? This class is painful. Derivatives, thank you. Okay? Same derivative. So that wordy, when the curves have parallel tangents, boils down to where do they have the same derivative? Well, I will need to find their derivative. Or where are their derivatives equal? Well, their derivatives are 2x minus 5. And what's the derivative of negative 2x plus 5? Negative 2. If they're going to have the same derivatives, then I need to say, when does 2x minus 5 equal negative 2? Well, that's at 3/2. Now what's going on here visually, the reason I had you graph this is, if you were to graph this, it's x minus 1, x minus 4, has roots at 1 and 4, it looks like this. The other graph is a downward sloping line, it looks like this. Now the line has exactly one slope every year, but the parabola has lots of slopes, here, 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 here. They're asking, when is this slope the same as that slope? It's right there.
Good morning, Devlin Jaguars. Please rise for the Pledge of Allegiance. Begin. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Please be seated.
The University of Missouri-Columbia is the birthplace of homecoming back in 1911. Mizzou will be visiting with prospective students today, September 13th, during 7 hours.
This was,
Honor roll students.
What is that?
Honor roll list.
that's wide up.
Make sure your name appears in the honor test marks. There's a name, please, that you cannot take them.
That one was terrible.
Seniors, we still have more space for baby pictures.
Next one
Make
is,
sure you submit and pay for your favorite pictures in yearbook link in the pictures you have had on the website. You can save for 3 pictures of your favorite child. You only have 2 more weeks to be involved in the yearbook.
Go check slide one here on the but don't forget to go to the sunflower Make sure you vote for your homecoming run.
yes.
Yeah, I do. Oh, that's
And the value, we wanted it at 0. Square root of 1 minus sine. Yeah, gosh, if your calculator is not in radians in this class, you are going to die. Not figuratively, not thought. Okay? All calculus is done in radians. So that should be negative 1. There's lots of documents.
Oh, okay, got it.
I will take that tomorrow. Yes. Because you have to specifically say in the definition of derivative or something like that, that's better to do it. I would put one in the calculator. I would put one in the